Welcome back to the course in nuclear medicine. Today we'll be looking at more basic concepts in the field. Specifically, we'll look at some of the most important things: characteristic X-rays and Auger electrons. These are fundamental to the spectrum of light that elements emit when they get excited. We'll also get a brief introduction to nuclides. These are the nucleuses of atoms that contain both protons and neutrons. And different nuclides, of course, are different configurations of protons and neutrons. Some are stable and some are unstable. And it's the unstable ones that eventually lead to radioactivity. If you enjoy this video, as always, like and subscribe to the channel. There'll be plenty of videos in the future, which I think you'll really enjoy, and enjoy this one as well.
Let's start talking now about matter, elements, and atoms. So really quick, I hope this is a review, but let's see how it goes. So atoms are composed of a nucleus, which is what I'm pointing out here. You guys don't see my mouse. That's this part in the middle. That is composed of protons and neutrons. And then we have atomic orbital electrons, in which we have electrons orbiting that nucleus. And in general, the atom is electrically neutral because you're going to have some positive charges in the nucleus. Those electrons are going to be negatively charged, but as a whole, you have the same number of positive charges as negative charges. So in general, they're going to be electrical neutral. Yes, we can end up ionizing atoms and getting them charged. We're going to get to that later. So these are the components of an atom. The nucleus is proton and neutrons, and I'm giving some information about their masses and their charge. So a proton has a positive charge, an electron has exactly the same value of the charge but is negative, and a neutron has no charge. And you can see how the electron is 4 orders of magnitude less heavy than protons and neutrons. And well, that number of protons is what gives us the information of what type of element is, and that's how we build what is called a periodic table, in which here we have all the elements that we know, and depending on the number of protons, we'll start filling them there. Molecules are when we can combine some of these different elements, so some nuclei that have different protons, the atom as a whole. If we combine different molecules or different elements, we create what we call a molecule. And here I just have an example of one that is very commonly used in nuclear medicine, but in which you see we're combining oxygen with hydrogen. We have a fluorine, we have something that we call a molecule. Now, this model of the atom is referred to Niels Bohr. Niels Bohr, I think he was a physicist. But he says, okay, we're going to think about the atom as being a nucleus and some electrons orbiting around. And what happens is that the electrons cannot just be anywhere in that atom. They have fixed shells. And the diameters of those shells are determined by quantum numbers. So we define different shells, and we call the K shell, the Al shell, the M shell, the N shell, and we assign a quantum number to each of those. So the K shell will be represented with n equals 1, L shell is with n equals 2, and so on and so on. And then each of those shells has a number of allowed substates. So for example, the K shell, and it has 2n-1. So the K shell will have only one substate, the L shell will have 3, the M shell will now have 5, and the maximum number of electrons that you can accommodate in each of the electron shells is given by 2n squared. Now, what's keeping those electrons orbiting around the nucleus? That's something that we call the electromagnetic force. We have positive charges in the nucleus, we have negative charges for the electrons. There's some attraction between those positive and negative charges, and that's why those electrons are bound to the atom. if I want to remove one electron from the atom, from an orbital shell, then I need to apply some energy. I need to put some energy into the process of removing an electron from that atom. So that energy that I have to put into the system to be able to do that is what we call the binding energy of an electron to the shell. So if you are going to remove an electron from the K shell, then we'll call that the binding energy of the K shell, or if you're going to remove it from the L shell, from the first substate, then you're going to need a different energy. But the point is that the innermost shell, which is the K shell, is the one with the highest binding energy. And then as we move from the center out, they have less and less energy. So the further away you are from the nucleus, those electrons that are further away are less bound to the nucleus. So does the binding energy increase or decrease with Z? Z, we're going to talk about that in a moment. So that's the number of protons. So if you think that you put more positive charges in the nucleus, then you're going to have a bigger force attracting those electrons. Why electron shells names are started from K and why not from A? I honestly have no idea. I think that's just a standard that people came up with a long time ago, and for some reason we just kept it. Yeah, I mean, that's just a convention that was adopted many years ago, but I don't have too much to say about that. So yeah, so those electron binding energies then is the energy required to move one electron from one shell to another. Okay, sorry. If I have then the nucleus and we have electrons around that nucleus and we have different shells, here I'm highlighting the K, the L, the M. I'm showing that the K shell can only fit 2 electrons, the L shell can only fit 8, and so on and so on. If we want to move one electron from one shell to the other, so for example, I'm bringing one electron from the K shell to the L shell, then the energy required for that is the difference in binding energies of the 2 shells. The ground state, when we talk about a ground state of the atom, is when we have the lowest allowed energy state of the atom, when all shells are filled in order from K shell out, depending on the number of electrons. So if you have 3 electrons, for example, you would put 2 electrons in the K shell, then you cannot put the 3rd electron out there anymore. You put the next electron in the L shell. So you start going in order, filling the shell. The lowest energy that you can have is what we call the ground state. An excited state is when the atom has more energy than the ground state, and that's when a shell has an empty spot that could be occupied by an electron from an outer shell. So that's what I'm showing here. So we have 1 electron on the M shell, but we see that we have several empty spots on the L shell still. So this electron could in principle occupy this space. It is out there because it's in an excited state. To make it go to the ground state, this electron would go down here. Ionization is a process in which an electron completely abandons the atom. So this electron, let's say it was here in the L shell. Something happened and that electron left the atom. So now we have more positive charges in the nucleus than negative charges outside in the orbitals. We have an ion, the atom is charged. That's what we call an ionization process. And then that brings me to something that is called characteristic X-rays. So so let's say that example that I had, we have an empty spot in a shell, and we have an electron in the outer shells. When this electron from the outer shell fills an empty space on an inner shell, there's a difference in energy because there's a difference in energy between those 2 shells. So where does that difference in energy go? Well, it turns out that that energy is released as a photon, is electromagnetic radiation. So it's a photon, is light. That difference in energy gets carried by something that we call an X-ray. And different elements in nature, well, they have different organizations of the different shells. So we call them characteristic X-rays because the energy of those different X-rays is very particular to that particular element, to that particular atom. By looking at the radiation, by the frequency or the wavelength, we're able to determine where it comes from. So we call this a characteristic X-ray. There's radiation coming from the filling of an electron from an outer shell to the initial shell, to an inner shell. And this has to do with a little bit of quantum mechanics, but the energy of that photon is related to the Planck constant and the frequency of that photon, or if you want to write that in terms of the wavelength, which is lambda, then it will be the Planck constant times the speed of light divided by the wavelength. There's also something else that can happen, is what we call Auger electrons. So keep in mind the process that I just mentioned. We had an electron in an outer shell. It's going to fill an empty spot in an inner shell. And we saw what we're just talking is that that process releases some energy as a characteristic X-ray. Like a competing effect for this is something that we call, okay, that energy, instead of going out as electromagnetic radiation, that energy can be transferred to another electron in the atom, and that energy is able to kick out the electron from the atom. This electron that leaves the atom is what we call an Auger electron. And the kinetic energy of the Auger electron is basically, well, it has to do with the binding energies from the different shells. So it will be the binding energy of the shell of the original vacancy. So in this case, for example, it was the A shell that was vacant at the beginning, minus the shell, the energy of the new vacancy, which now we have a new vacancy in the M shell, plus the shell of the new vacancy too, which now we have a vacancy, another vacancy in the L shell, because that was the electron that left. So that's two processes again. We have either characteristic X-rays or either Auger electron. They are competing processes that it depends a little bit on the specific element and the shell. The probability of whether an X-ray is emitted or an Auger electron is emitted is something that is related to what we call the fluorescent yield. And the fluorescent yield is a probability that when you have these events, because they're competing, what's the probability that you actually end emitting a characteristic X-ray? So if you plot that, you'll see that the fluorescent yield becomes higher. So the probability of getting an X-ray instead of an Auger electron goes higher as you increase the number of protons in an atom. So let's see, I have some other questions just to make sure that we are understanding. So how many electrons can occupy the M shell? So remember, M shell is KLM. And okay, I'm gonna give 5 more seconds. Okay. So it says, so most people got it right, but I see that there's some, I mean, B and D are still very equal. So M shell is KLM. So we assign an N equals 3 to the M shell. And we said that the number of electrons that can fit in a shell is 2n squared. So N is 3 squared, 3 squared is 9, times 2 would be 18. Okay, so the real answer here, the correct answer is C.
I didn't see you with the red sign around it. Do you mind doing it? Just it's captured in the recording. It's okay, thank you.
Sorry. The correct answer was C here. So let's look at this one. Order the atomic shells from lower to higher energy binding, sorry, to higher binding energies for the electrons occupying them. So lower energy to higher energy. And I'm gonna give 5 more seconds.
Maybe another 5. Just, I think people are entering.
Okay, so yeah, sorry. Most people answer D. That is correct. So A is not correct because K is the shell that has the highest binding energy. It basically cannot be smaller than anything else. So yeah, so correctly is D. You start from the outside and go in. And that's because I said from lower to higher binding energies. Okay, are there any questions so far before we start talking about the chart of nuclides? Let's start talking about this. I think we have like 5 minutes and we can continue on the next lecture. So what is the chart of nuclides? So we've talked about protons, we talked about neutrons, but when we talk about a nuclide is basically characterized by the exact nuclear composition. We're interested in the atomic number, Z, the neutron number, and the mass number is something that we label as A, that is basically the sum of protons plus neutrons. So when we represent a nuclide, we typically have this notation. Sorry, let me just take a little laser. So we have our nuclide X that is composed of Z protons and neutrons and has a mass A that is Z plus N. And let's imagine that we're gonna, okay, and yeah, and one important definition, one important characteristic of what we call the nuclide is that it must exist in nature for more than 10 picoseconds, 10 to the negative 12 seconds. If it doesn't exist for at least that long, then we're not gonna consider that as a nuclide. But let's think on a plot in which we're gonna put the number of neutrons on the x-axis and the number of protons on the vertical axis. And we can define some properties, okay, some characteristics in this chart. So we call an isotope nuclides that have the same proton number. So if you look at this graph, protons go in the vertical axis. If they have the same proton number, they're gonna be a horizontal line. Because they have the same proton number, then they are the same element. So that's why I here call X, X, X. They all have the same Z number, but they can have different neutron numbers. So they're gonna have different masses. So they're isotopes of the same element. They all have the same proton number, but they have different neutron number. We can also call something, we also define something that we call isotones. And isotones are nucleids with the same neutron number. So I mean, just take a look here. I'm highlighting P because it goes with proton. Here I'm highlighting N because it goes with neutron. Now, if they have the same neutron number, they're gonna be a vertical line in this plot. But if I have a vertical line here, it means that I'm changing the proton number. So if I'm changing the proton number, it's going to be different elements. So that's why I have one that we label X and one that we label Y. This one has Z1 protons. It has the same neutron number in both, but then that results in different masses because of the sum. And we also have something that we call isobars. Okay, this one, I'm highlighting the A because it's related to the A of the mass. And these are nucleids with the same mass number. So A stays constant, but Z might be different and N might be different, and that which is going to look like a diagonal line in that chart of nuclides. Well, we know about 3,000 nuclides, but then what we see in nature is that only few of those are stable. What we mean with this is only few of them stay in the same composition as we see when we find them. Most of them become different things, they become different elements, so they are non-stable. And when we plot these from all those nucleids that we know in nature, okay, the red line that I'm showing here is when the number of protons is equal to the number of neutrons. When we plot all those that we know, we see a curve that goes like this. So And then we also see that this dark line in the middle is what we call, well, you can see how much the different colors indicate how long will those nuclides exist for in nature. That darker one, the darker line in the middle, is the ones that live the longest, is what we call that they are very stable nuclides because they really don't change. But then something really interesting that hopefully it catches your eyes there, but then the question becomes, okay, if this red line is where the same number of protons and neutrons happen, we're seeing that most of our nuclides have more neutrons than protons. So then it becomes a question, okay, but why do we have more neutrons than protons? Would anyone be able to give an idea of why would that be? Is it true to say in general any atom except the isotope is a nuclide? So a nuclide is talking about the nucleus. So forget about the atom. A nuclide has to be just focus on the nucleus and remove the electrons. So when we talk about a nuclide, we're looking at that composition of that nucleus. And then you just have some of those nuclei that have the same number of protons in between, but they have different number of neutrons. Those are isotopes, but they're all nuclides. Is 3,000 the total number of all elements, including their isotopes? Isotope number of total elements. Okay, so the number of total elements is around 118. That's different than me saying we know about 3,000 different nuclides, because we can have, let's say, one element, one fixed Z. I can't come up with a big example right now, but you can have many, many different isotopes for a same element. So you can have, let's say, Z equals 18, but you can have 18 neutrons as well, or 19 neutrons, or 20 neutrons, or 21 neutrons. You can have many, many more isotopes for the same element. So that's why in total, we know about 3,000 nuclides, 3,000 different configurations of nucleus on different elements. Okay, and then someone is saying, okay, so I'm asking the question, why more neutrons than protons? And I think someone just answered, because neutron acts like glue in big nuclides. Okay, so why do neutrons act like glue? What is making those neutrons act like glue? So should we leave it there, or do I have 10 more minutes?
How many more slides do you have?
No, this is going to cover, I think, today and Thursday. So
I think you should answer this question, and people are starting to talk about the strong nuclear force.
Yes,
I
exactly.
think we could try to, just for everybody to know, we had mentioned these classes are for 90 minutes, but technically we should really try to finish 10 minutes in advance in case people have other classes to attend. That's why we will try to end by 10:20. But why don't you just explain a little bit and then we can wrap.
Okay, so let's finish this. So yeah, so I think people are starting to go in the chat and they're going in the right direction. So in nature, we have 4 fundamental forces. And we see that gravity, we have something that we call the weak force, we have something that we call the electromagnetic force, and we have the strong force. And if you rate them from order from weakest to strongest, then it will look like that. The strongest is the strong force. And these 4 fundamental forces that occur in nature, comes from something that is called the standard model. And in the standard model, we have quarks and leptons, but we have some very interesting particles that we call bosons, which are these ones that I'm showing here on the right. And basically, each of those forces is an exchange of bosons. So for example, electromagnetic force is when we have 2 charges, a positive charge and a negative charge, and they start attracting to each other, is because those particles are exchanging photons. When you talk about gravity, and this in principle was a discovery that didn't happen that long ago, let's say the sun and earth, the earth is orbiting around the sun because of the gravity. It's because the sun and earth are exchanging what we call a Higgs boson. When we talk about weak forces, is because those particles are exchanging Z or W bosons. And when we talk about a strong force, is because particles are exchanging gluons. So what happens is the strong force is very, very strong, with that exchange of gluons, but the range in which you can feel the strong force is very, very small. However, gravity is not very strong, it's very weak, but it can cover distances from basically the sun to Earth or the sun to Pluto. And when we talk about electromagnetic, well, electromagnetic has also a very, very big range. So when you are forming a nuclide, if you put a proton and another proton and you start bringing them close together, they're both positively charged. So there's going to be an electromagnetic force that's going to be pushing them one. It's going to push one out from the other. It's going to be repelling. But as you bring them closer and closer and closer together, again, keep in mind, I'm talking about the strong force now. The strong force has a very short range, but if you're able to get them into that close of a range, and I think that's in the order of femtometers, then the strong force is way, way stronger than that electromagnetic force. So that strong force ends up counteracting that repulsion. Now, if you bring another proton, then yes, you can have some more strong force, but then there's also going to be an electromagnetic force. And if you start putting protons, then there's always at some point the electromagnetic force, either because of the size of the nucleus, just going to be able to win the battle against the strong force. But to counteract that, then that's where neutrons come in place. Neutrons do have that strong force interaction with protons and with other neutrons. So the more neutrons you add, you start balancing that electromagnetic force from those charged protons, and then that strong force is higher in magnitude that ends up holding those nuclides together. So that's the reason why we see that as we move forward, you need more of those neutrons to hold those nuclides together.